Over 300 million food cans are formed, filled, and sealed every day. Here's how thin steel survives heat, vacuum, and overpressure without failing. If internal pressure drifts by just 20 mbar, sterility collapses before cooling even starts. Let's step into the line. 3 pressure points decide everything: forming, double seaming, and retort cooling. Each fails in a different way, and each must stay inside its own tolerance window. Today we follow the chain end to end. Forming, welding, filling, vacuum, seaming, and thermal sterilization. A coil of tin-plated steel unrolls at high speed. Blanks are punched out and deep drawn into cylinders. Drawing shapes the base. Ironing then thins the walls, cutting thickness almost 50%. The body stretches from a flat blank to roughly 120 millimeters tall. Punch load is sampled at 1 kilohertz. If force spikes even briefly, micro tears form that later fail under retort pressure. If wall thinning exceeds plus or minus 5%, the body collapses during sterilization. Sidewalls close and pass through electrodes at over 100 meters per minute. Current fuses the seam into a continuous weld without melting the steel. Cooling is critical. Temperature must fall from 1,100 degrees Celsius to below 350 degrees Celsius in 0.15 seconds. Any slower, and voids form inside the weld. An eddy current sensor checks weld integrity. A 0.1 millimeter defect is enough to leak under retort overpressure. If cooling misses the 0.15 second window, voids form and the can leaks downstream. Product enters through precision flow valves. Fill weight tolerance sits around plus or minus 1 gram. The key is head space, the 6 to 10 millimeters of air above the product. Too much air lowers vacuum later. Too little causes lid distortion under pressure. Steam injection replaces oxygen with saturated vapor. Headspace oxygen must stay below 3%. Above 5%, spoilage risk rises exponentially within weeks. The lid meets the body. 2 rollers fold and lock 5 layers of metal into a hermetic seal. Target seam thickness, 1.0 to 1.3 millimeters. Tightness, 50 to 80%. Hook overlap, 50 to 70%. Vision systems measure each parameter in real time. A single micron of drift changes pressure retention, and the seam fails under sterilization load. When the hot can cools, internal vapor condenses. This creates the stable vacuum that protects the product. But the vacuum only forms if headspace, seam tightness, and temperature align. If cooling starts too early, pressure equalizes and vacuum collapses. Cans enter the retort, a pressurized sterilization chamber. Temperature rises above 121 degrees Celsius. Pressure sits between 1.4 and 1.8 bar to keep cans from deforming. Internal and external pressure must match within a 20 millibar window. If external pressure is too low, cans swell or burst. If it's too high, seams buckle inward. Cooling is staged. Pressure drops in controlled steps to prevent vacuum shock. This is the moment that determines sterility for the product's entire shelf life. Retort pressure drift beyond plus or minus 20 millibars causes swelling, buckling, or incomplete sterilization. Every station is pressure matched from start to finish. Sensors track punch load at 1 kilohertz, weld temperature at 200 hertz, seam parameters every cycle, and retort pressure in 1 millibar steps. Corrections fire automatically before operators ever see a warning. The entire system stays inside a synchronized plus or minus 20 millibar differential, from forming loads to retort overpressure. 5 pressure systems align into one outcome: a sterile, shelf-stable can that survives transport, storage, and years on the shelf. If you want the high-speed version, DWI beverage cans or aseptic pouch systems, tell me which line to unlock next.